Good morning, everybody. Our next topic in calculus is our last one with applications of a derivative. It's in section 9.2. It's a little bit out of order, but it's a great place to fit this. It's called L'Hopital's rule, and sometimes there's an S there, so people call it the hospital rule. But it's really pronounced L'Hopital, and I'll run through this. You can check the textbook. Right? They talk a little bit about how to do this. So if there's anything they don't explain well enough, check that. Email me. I'm on email all the time. All right, so I'll get right back to you. I can add just email back an answer, or do another video to help try to explain something, or we can set up a Google Meet where we can discuss it. So, all right, you have lots of options there for how to reach me. So please take advantage of that if there's anything you don't understand. Okay, so L'Hopital's rule, and this is just basically right, to sum it up. If somebody has said, "What is L'Hopital's rule?" It's just a technique for evaluating limits. Okay, so we're kind of going back to limits in this. And as you look at this, it's going to actually be much easier than what we did before, because you may or may not remember from limits, right, that we had, as we were doing these, right, we had all these different rules for what to do in different situations, and L'Hopital's rule is going to use derivatives to help us make limits a lot easier. So we couldn't do it before because we didn't have limits. We didn't have derivatives. Now we can, because we know how to do derivatives. Next year when you take college calculus, you're going to use this, and this is going to make everything easier for you. It's kind of like cheating because you're going to be doing things out of order, right? But if you use L'Hopital's rule, you'll get a lot of these answers. So this is really a nice technique. Okay. So just to remind ourselves, right? How do we evaluate? Limits? And you may remember that sometimes you can just look at a graph. Right? That's the easiest way, really. If you have a graph given to you, just try to trace it to where it's going to be, right? So if you had something like this, right, and the graph was like doing something like this, right? And we know that x value is 1, and it said find a limit as x approaches 1 from the left side of this function. You would just trace from the left side of 1, and you say, oh, it's approaching infinity for ourselves. So remember that's graphically. Right? Another easier way to do, if you're given a chart, you can just have a chart. So if there's like a whole bunch of numbers there, right, you kind of just trace the chart and see what the pattern is going to be. The most common way was just to do, was just to plug in the c to the given function. Okay, because a lot of times the limit equals the actual value. Remember, the limit is the value you're approaching, and a lot of times it equals the actual value you're going to have as well. Right? There were some other lesser known techniques, right? And a lot of times we couldn't plug in c initially, so we had a lot of simplified fractions, then plug in c. Right? We had some where you just had to know a rule, and one we had to know a rule was like the limit as x approaches 0 of sine of x over x, right? That was one where you're like, oh, we just know that equals 1, so we did that every time. But really, this one, right, is going to be the best one here. This one is actually going to help, because if you know L'Hopital's rule, you can not know this, and you can a lot of times avoid that simplifying fraction. So it's going to really replace these two, and it's going to make it a lot easier. So really, you're just doing, once you know this rule, you're going to be able to plug in c to get the function. If that doesn't work, you're going to use L'Hopital's rule. This is going to be like a miracle worker here. Okay. Now, L'Hopital's rule, this only applies if you're evaluating a limit, and when you do it, you plug into your function. You have two pieces to it, a top and a bottom, and if it gives you 0 over 0 or infinity over infinity. Okay. Both of those, you may or may not remember that 0 over 0, when we did this, we said, hey, that tells you something. That means that you could simplify it. So that's a lot of times when we simplified the fractions or we knew a rule, was because, hey, we had 0 over 0. That meant we were missing something there. Infinity over infinity is ambiguous, because just because they're both approaching infinity, we don't know how quickly they're approaching infinity, so we had lots of different answers. It could be 0, it could be a finite number, it could be infinity. So, right, these two were the ones where you just had to do more. You had to look back at the original function and kind of do some work for it. And right, that's where L'Hopital's is gonna help us out. Okay. So let me just show you how this works. All right, and you can just watch the notes. You don't have to write all this down for yourself. If you want to, you can, right? But let me just show you where this comes from. So remember, we're starting with this function f of x over g of x. Okay? So this could be like sine of x over x, something like that, or 1 minus cosine of x over x. Lots of options for ourselves as we do this. Okay? And just want to remind you that if I take a fraction and I divide both the numerator and denominator by the same thing, and don't worry, this is not anything you're going to have to prove, okay? I'm just going to show it to you. If I divide them by the same thing here, all right, I'm going to divide them both by x minus a. And by the way, a is going to be, let me make that c for myself, because c is what I'm approaching there, so that's going to be a little bit better, okay? Right. These two are equivalent because basically you take a function, if you divide them both by the same thing, both the numerator and denominator, it's going to be the same fraction for ourselves. Okay? So, I want to remind you, and remember that we had this condition that the top function and the bottom function were both can equal 0. So, and f of c equals 0 and g of c equals 0, right? That was one of the conditions. We could have also done this with infinity. It's a lot easier to prove with the 0. Okay? So, because these are both 0, then this is true as well. Okay? Why is that true? Because we're just subtracting 0 from the top and the bottom, so nothing's really changed there. All right, we have our function the same. Okay? So we have this, and this was under the condition that we're approaching the c value for ourselves. Okay? Well, if we look at this, these right here, these are both y values, right? So this right here is the change in y. And this right here, these are both x values. This is the change in x. If we look at the denominator there, that's the change in y, and that's the change in x. So we can see we have these change in y over the change in x for the numerator, and the change in y over the change in x for the denominator. Hey, these are slopes, right? Change in y over change in x is a slope. So it's the slope of this function. This is the slope of this function. What does that mean? The slope, that's the instantaneous rate of change. So this is really the derivative of the function. Okay. Over the derivative of this function. Whoops, that's g. Okay. So as long as we have the condition that f of c and g of c equals 0, then the limit that this function is approaching, right? I should put a limit as this function, okay? The limit that this function is approaching, and we just simplified, is going to equal the limit that the derivatives approach, all right? And that's basically what L'Hopital's rule is. Okay? If the limit as x approaches c of f of x over g of x equals 0 over 0 or infinity over infinity, then the limit of the original equals the limit of the derivatives of the functions, okay? Now, you may look at that and say, whoa, I didn't get all that theory behind it. And really, that's okay if you didn't get all the theory. The important thing is that you have this down right here, right? This is what you need to know. Hey, here's L'Hopital's rule for ourselves, okay? Right? This is true because as I did this, Again, we knew that it was 0 over 0. We had that condition at the beginning, 0 over 0. Right? We took f of x and g of x, we divide them by the same thing. Fractions are the same. If you divide both the numerator and denominator by the same thing, you haven't changed anything. Then we subtracted 0 from the top and the bottom. Didn't change anything, it's just subtracting 0. We looked at this and said, hey, this is the change in the y's, that's the change in the x's. This is the change in the y's, that's the change in the x's. Change in y over change in x, that's slope, which is the derivative. This is the slope, that's the derivative. Okay? So, right, that was our theory. This is the proof right there, but this is really what you need to know, right? And that's what we're going to do some examples on in the next video.